recording. All right, welcome back. So just a couple of reminders and then we'll get started with the material. On Thursday, you guys will write the first of the two term tests. So the term test for Thursday is on lecture sets 1 and 2. So it's basically a review of regression analysis, which hopefully will follow from what you did in the projects. And it also includes basically details on the framework for which a random variable would fit into the GL. It includes questions about how we would determine if a random variable would fit into a GLM framework, and basically, mathematical problems designed to test your understanding of how to put densities or random variables density functions into the exponential family, and how to evaluate the properties of those random variables given they belong to the exponential family. And then there's some definitions and whatnot associated with those ideas. So that's going to take place Thursday via CrowdMark. So it'll run during lecture time. So you'll write the test from 11 to 12:20. And then I'll basically bake in an extra 15 minutes at the start and at the end to give you time to access the quiz in case there's any issues and to get your photos taken and the answers submitted. All right, so it'll basically be 10:55 until 12:30, and that is inclusive of everything. So finishing the quiz and posting all your solutions. I posted on Friday, I believe. Yeah, it was on Friday. Like a practice problem set or a sample test. It was a sample term test, or is a sample term test. And this is, I would describe as reflective of what you're going to see on Thursday. So in terms of number of questions, it's pretty much identical. In terms of structure, it's very, very similar. So I encourage you to work through that term test before tomorrow's lab. And during lab tomorrow, what I'll do is I'll go over the test with you and work through the questions so that you have a solution set to them. And then that way, if you've already worked through it, you can also check your answers, which of course can be helpful so that you know kind of where you may be struggling. All right, so the second term test will be a month from Thursday, and then that will cover, from lecture set 3 until, probably where we leave off before the reading week or something like this. I'll give an exact lecture set coverage once we get closer to that date, but it'll certainly start at lecture set 3 and it'll probably end somewhere around lecture set 5 or 6. So probably something from estimation for GLMs through to at least binomial GLMs. All right, any questions about the term test or that plan? All right. Okay, so we're going to start, or we're going to continue with lecture set number 5 today. We're getting close to the end of lecture set 5. It's been a pretty heavy, or lecture set number 4, sorry. And we'll start lecture set 5 once we finish this material. Lecture set number 4 is about inference for the GLMs. It's been a pretty heavy lecture set mathematically. We've looked at a lot of different examples for those 3 main distributions that we've discussed throughout the course. So the normal, the Poisson, the binomial. Right now, what we're in the process of doing is deriving expressions for the deviance measure. So the deviance is one of the key goodness of fit statistics that are utilized for GLMs. And essentially what the deviance does is it allows us to compare the model of interest to the saturated model, which, as you might recall, is the model that has one predictor for every single observation that's in the data set. The deviance, as we showed last class, is a chi-square random variable. So once we've computed the deviance, we're basically just tasked with comparing it to a chi-square random variable on the associated degrees of freedom. And then we can use it to test whether or not the model of interest is sufficient against the alternative that the maximal model is required. Okay, we've driven. So after going through the process of basically deriving the general expression for the deviance, so you might remember that it's basically just the log of the log, it's the log of the likelihood ratio statistic multiplied by 2. After going through the process of deriving that estimate, we are now looking at the specific forms of the deviance for the different distributions that we're going to study in the class. So we looked at the binomial expression last class. So we drove that before we got to this example. And right now we're looking at the expression for the normal linear model. Now, with the normal linear model, there's also a few other details that we can attach to our deviance estimate. I'm going to go through those momentarily. Then what we'll do is derive an expression for the Poisson distribution. And then following that, we'll look at an actual example of how we can utilize the deviance to make a statement about the goodness of fit of a particular model. So we're going to finish the normal, then we'll start the Poisson example, then we'll look at an empirical example. And then the last thing we're going to do in this lecture set is talk about hypothesis testing to compare two different GLMs. So again, with the deviance, we're comparing a model of interest to a saturated model. The last section of this notes or of this lecture set is going to give us an idea of, or an example of how we can compare two different GLMs with different subsets to one another. So this would be sort of like an extra sum of squares F test in the linear model case, which is actually what we're going to basically arrive at when we get to this illustration. Once we finish that, we'll move into lecture set number 5. Lecture set number 5 is the first lecture set where we're actually going to study a specific type of GLM. So we're going to start, or we're going to discuss one of the most common binomial GLMs, which is the logistic regression model. So this model has many different names, and I'm sure you have probably seen it before. I know if you've taken multivariate, Sue covers it for a while in multivariate. If you had taken, there's a third-year class with Karen. I don't know, the name escapes me, but it's basically about count analysis, and you would have seen it in there as well. So we're going to talk about basically the model fitting, or how we would formulate and fit that model via maximum likelihood estimation. And then we're actually going to look at empirical examples and learn how to interpret the model, evaluate the model, how we would work with the model, that sort of thing. So we're going to start to transition a bit more to the data analysis side of the course, which is great. Because we've been pretty bogged down in theory for the most part over the first month. Okay, so with all of that being said, let's get started here. All right, so we drove an expression for the deviance for the normal linear model. Again, this is basically the difference between the log likelihood of the maximal model and the log likelihood of the model of interest. And we can use the deviance to determine if there's evidence that we actually need this maximal model. Now, a few subnotes just related to this derivation. So we have the expression above. The deviance is 1 over sigma squared times the sum from I equals 1 to n of y minus mu hat I squared. Okay. So this is the general expression for the deviance in the simplest case, where we have, where this is an expression for the deviance that we can use to evaluate a normal linear model. Just a couple of side notes here. Okay. If the expected value of yi is equal to mu, okay, for I equals 1 to n, okay, then beta hat will be equal to mu hat. Right? Which is equal to y bar for I equals 1 to n. Okay. Therefore, D is equal to 1 over sigma squared times the sum from I equals 1 to n of yi minus y bar squared. Okay. And then recall that s squared is equal to 1 over n minus 1 times the sum I equals 1 to n yi minus y bar squared. Okay, so therefore, s squared is equal to sigma squared d divided by n minus 1. Right? Okay. And then we can say since n minus 1 s squared over sigma squared is a chi-square on n minus 1, then d is a chi-square on n minus 1. Okay, so that's the first note. Okay, the second note. Okay, so here we can say so recall that d is equal to 1 over sigma squared times the sum I equals 1 to n of yi minus xi transpose beta hat squared. This is the same thing as 1 over sigma squared y minus x beta hat y minus x beta hat transpose. Okay. Since y minus x beta hat is equivalent to y minus x transpose x inverse x transpose y, which is equivalent to the identity matrix minus x transpose x, this is inverse, X transpose Y which is equal to I minus the hat matrix oh no, sorry. Then D is equal to Y bar transpose I minus H Y. Okay. And this is distributed chi-square n minus p. Well, I should say this is distributed chi-square n minus p since the rank of I is equal to n and the rank of H is equal to P. Okay. All right, so just a couple of quick properties relating to the deviance of the normal distribution. Does anyone have any questions? Recording, right? Okay, so now what we'll do is we'll look at a similar derivation for the deviance of the Poisson model. So we're going to derive the deviance expression here, and then we're actually going to look at an empirical example where we utilize this value. Right? Okay, so the starting point for this is the same as the derivations of the deviances for the other distributions that we have studied so far. So first off, let's just quickly write down the PDF for the a Poisson model. So we're going to have f of yi is equal to lambda I to the yi over e to the negative y, or e to the y e to the yi over lambda I factorial. E to the negative lambda. Oh boy, not good. Okay, so it follows from this that the log likelihood of lambda I given yi is going to be equal to the sum from I equals 1 to n of yi log lambda I minus n lambda I minus the sum I equals 1 to n of log yi factorial. Okay. So for the maximal model, we have lambda I for I equals 1 to n. Okay. So beta is equal to lambda 1 through lambda n transpose. Okay. The MLEs are lambda I hat equals yi. Okay. Therefore, L beta hat max given y is equal to the sum from I equals 1 to n yi log yi minus this would n lambda I becomes n yi. I have to transform this back, so this is going to become the sum I equals 1 to n yi minus the sum I equals 1 to n log yi. I'll just put the sum back in here for now because it's a little more consistent. And actually, I couldn't do n times lambda I anyways because the lambda i's are all different. So it would have been the sum of the lambda I. So that should be a sum, not a little n. If the lambda was constant, then we could write n times lambda. Okay. All right. So let the model of interest have p less than n and MLE beta hat. Okay. MLE beta hat. Then we can write yi hat is equal to lambda I hat, since the expected value of yi is equal to lambda I. This gives L beta hat given y is equal to the sum I equals 1 to n yi log yi hat minus yi hat. minus the sum of n factorial. Okay. Therefore, the deviance is equal to the sum from I equals 1 to n yi log yi over yi hat. Or sorry, 2 times the sum minus the sum of yi minus yi hat. Right. Okay, and then we can say, since the sum of the yi is equal to the sum of the yi hat, then d is 2 times the sum from I equals 1 to n of the yi times the log of the yi over the yi hat, which is sometimes also written as d equals 2 times the sum I equal 1 to n oi log oi over ei, where oi are the observed values and ei are the expected values. Right. Therefore, d can be calculated from the observed data and fitted model where d is distributed chi-square n minus p. All right. Any questions? Okay. Check something. All right, so if there's no questions, we'll look at an example of utilizing the deviance now. Okay, so you might recall from lecture set number 4 when we talked about fitting the Poisson GLM with identity link, that to illustrate that process, we use the following example data. So we're going to use the same data set now to illustrate the calculation of D and assessment of the goodness of fit statistic, which is D. Okay, so from that process, sorry, there's an extra 3 here. Shouldn't be there. So from that process, we found that yi is equal to 7 point, or the estimated model has beta 0 hat 7.45163 and beta 1 hat 4.93530. Okay, so we want to compute D and then assess the goodness of fit. So the first thing we need to do are actually work out the yi hat. So given the fitted model, it's very easy to work out the yi hat. We simply have to plug in for each value. So when x equals -1, yi hat is equal to 7.45163 minus 4.93530, which is 2.51633. When x is equal to 0, yi hat is equal to 7.45163. When x is equal to 1, yi hat is equal to 12.38693. So the deviance is 2 times the sum from I equals 1 to n two times the sum from I equals 1 to n of yi log yi over yi hat. Okay, so this is going to be, for example, 2 times, and then we would have 2 multiplied by log 2 over 2.51633. Okay. And then we would have, for example, plus 3 times log 3 over 2.51633. And then, for example, we would have 6 times log 6 divided by 7.45163. And then we would just keep working this down to the last value, where we would have 15 times log 15 over 12.38693. Just make sure I did that correctly. Okay, so that should give us 2 times 0.94735, which is equal to 1.8947. Okay. Any questions? Cool. All right, so basically what would happen now is we would assess the fit of the model using the deviance. So like basically the way that this would work is if we think about a formal hypothesis testing procedure, we would have H0, the model of interest is sufficient versus HA, the maximal model is required. Okay, so again, with the deviance measure, they're basically always comparisons between whatever model you're fitting and the maximal model. We're going to look at illustrations of how to, well, when we start fitting GLMs in R next week, we will see output that gives us these residual values directly. So it's going to give us, or sorry, that gives us the deviance directly. So the R output is giving us the deviance for the comparison of the model of interest versus the maximal model. It actually also gives you the output for the null model, which is the model with no predictors, against the maximal model as well. But the point is that the deviance is actually a model comparison statistic that always compares the model of interest to the maximal model, right? Okay, so then on step 2, if we follow kind of like the way that I do hypothesis testing, we would declare a significance level. So we'll just use the standard. So let's just say 0.05. Okay, so then on step 3, we have our test statistic, which is the deviance. So in our case, this is the 1.8947 that we computed on the previous slide. Right. All right, now on step 4, basically what we're doing here is we're just comparing this value to the associated chi-square value on n minus p degrees of freedom. So for example, like if we were to sketch out a chi-square distribution, and then we were to mark down where the deviance is, right? Okay, so this area here is going to be the p-value for this hypothesis test. So we're going to have the p-value is equal to the probability that a chi-square is greater than 1.8947 because the deviance is chi-square on n minus p degree of freedom. So from R, for example, and again, we're going to show how this is true. You can actually find the p-value directly. So we can show that in this particular case, the chi-square, which is going to be on n minus p degrees of freedom. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 observations minus 2 parameters is equal to 7. Okay, so this p-value is going to be 0.9654, right? I'll just say this is on 7 so that we're clear. Okay, so basically then what would happen is, given the size of the p-value, we do not reject H0. And then on step 6, we can say at the 5% significance level, the data provide sufficient evidence to, the data do not provide not provide any evidence to suggest that the maximal model is needed. So it's kind of nice because we just fall back into sort of a traditional hypothesis testing approach. And in this case, we're almost kind of like hoping that we don't find evidence to reject the null, because that would imply that the model we fitted is a good fit to the data. Any questions? I mean, essentially. So I'm going to basically go through the process of comparing two models now, but it is like, as you described, it's basically you take the difference. So you have the deviances, which are both chi-square n minus p. So you take the difference between the two deviances, and then you end up with a the difference between the deviance is now going to be chi-square on p minus, let's say, q, where q would be the number of parameters in the other model. So once you have that value, the difference in the two deviances, you can just compare that to a chi-square p minus q, and then you can make the same assessment. Does that make sense? Yeah. So I think in that case, like basically what would happen is when you do the difference, you're testing the so the alternative is always going to specify the larger model. So the differences, or the difference in the deviances should be, in all cases, the difference between the larger model and the smaller model. So the bigger that difference in deviances, the more evidence there is that you need the bigger model. But I'll show you an illustration of this momentarily. Sorry, any other questions? Okay, so just a couple of quick notes. When we replace mu with mu hat, we have sigma squared d is equal to, well, we have the formula shown here that we drove before, right? So this is sometimes called the scale deviance. We'll write that the model fits the data well when d is approximately a chi-square on n minus p. And we just saw an example of how we can evaluate that. Okay, so since the expected value of a chi-square on n minus p is n minus p, then the expected value of d is also n minus p. So basically, we can also say, like, if d is close to n minus p, this would be an indication that I believe that would be an indication that the full model is needed. I'm just going to confirm. Yeah. So basically, like, if the value of d is small relative to the associated degrees of freedom, so if the value of d is small relative to n minus p, that's typically going to be evidence or a lack of evidence that the full model would be needed. But once the value of d approaches the degree of freedom, that would be an indication. Typically, I believe that would be an indication that the full, or no, it seems okay. So if the value of d is close to the degree of freedom, that would still give the same amount of evidence. Okay, because the expected value of d is going to be near the mean of the distribution. So you should have like roughly well, you wouldn't have like necessarily 50% on each side because it's a skewed distribution. But the point is that if D is close to the degree of freedom, so if D is close to n minus p, that would still be typically would result in lack of rejection of the null. Okay. Okay, so with that being said, we can also write an approximation of sigma squared hat that says sigma squared hat is the sum from I equals 1 to n of yi minus mu I hat squared over n minus p. Okay, we can also show that since the yi, we can also show that the deviance is related to the sum square of the standardized residual. So the sum of the EI squared is approximately equal to 1 over sigma squared hat of the sum from I equals 1 to n yi minus mu hat. And we would expect that the model fits well if the sum of these residual terms squared is equal to n minus p. Okay, so just a couple of different ways of also evaluating the test or evaluating the model is the point of these two slides. All right. Okay, so now what we can do is talk about model comparison. So this goes back to the question that was just asked. Can we take the deviance for the two models and figure out which one has the larger one and then utilize that? So the answer is yes. And the way that we would do that, again, we can structure through a formal hypothesis test. So let's suppose that we have a model with Q predictors and a model with P predictors. Okay, so both Q and P are less than N. So these are, neither of these are the maximal model, but Q is also less than P. So in the null hypothesis, we're basically saying the smaller of the two models is a sufficient fit to the data. And in the alternative, we're saying the larger of the two models, still not the maximal model, is required. All right. We can test H naught versus HA by using the difference between those two deviances, right? So we have delta D, the difference between the deviances is 2 times the log likelihood of the model given beta 1 hat, so the larger model, minus the log likelihood of the model given beta naught hat in this case. So we're saying beta naught, like vector beta naught, refers to the smaller of the two models. Okay, so if both models are a sufficient fit to the data on their own, then D naught will be approximately chi-square on n minus q, and D1 will be approximately chi-square on n minus p. So the difference between the two will be chi-square on p minus q, right? So basically, if delta D is consistent with a chi-square p minus q, we would recommend the smaller model. So essentially what we can do is we can use delta D in the same way that we had just illustrated to test whether or not there is evidence that the larger of the two models is required. And we would conduct this test using a chi-square distribution, except that the degree of freedom for this chi-square would now be p minus q. So the process is pretty much exactly the same as what we just saw, except that the degree of freedom for the chi-square is now changed. And then if delta D ends up in the rejection region, so basically if delta D is very large relative to the chi-square value of interest, so the chi-square on whatever significance level it is you're testing at on p minus q degree of freedom, we would reject the smaller model in favor of the larger model. Any questions? Okay, so let's look at an illustration in the context of the normal linear model. In general, I think that using this testing procedure is pretty straightforward because, again, you're just running a chi-square hypothesis test. The only requirement is that the one model would be a subset of the other model. Well, the one model would be a subset of the other model, same length function and same distribution. All right, so let's say we have a normal linear model. Actually, does it need to be a subset? I'm going to come back to that point. It might not have to be a subset, but that would make sense because that would be consistent with the other types of tests we've seen in the past. Okay, anyways, I'll come back to that idea later on when we look at more examples. Okay, so we'll return to the normal linear model. We drove the deviance for this model that's given below. Let's suppose that we have two different models, M0 and M1. So M0 has mean mu hat I0 and M1 has mean mu hat I1. All right, if M1 fits the data well, then D1 is going to be chi-square M minus P. If M0 fits the data well, then D0 will be chi-square M minus Q. And the difference between them will be chi-square P minus Q. Okay, let's suppose that the sum of squares for M0 and M1 are S0, 658,770.8, and S1, 652,442.5. How can we compare M0 and M1? All right, so in this situation, we have the following. So this actually dates back to what we discussed at the beginning of the class. So we have H0, M0 fits well versus HA, M1 is required. Okay, so let's say that we test this, 5% significance level again. And then on S3, we require delta D. Okay, to compare M0 and M1, we need to eliminate sigma square from D0 and D1. Okay, so recall that D0 is chi-square n minus P, I think we said. Yeah, or n minus Q. And D1 is chi-square n minus P. Okay, then we can write that F is going to be D0 minus D1 over P minus Q divided by D1 over n minus P. And this thing will be F distributed on P minus Q and n minus P. Okay, because when we take the ratio of two chi-squares, we end up with an F distribution. So this is basically just an example of an alternative way that we can compare two models. In this particular situation, we can't get delta D directly because of the presence of sigma squared, but there's a workaround where we can actually divide out the sigma squared term. And because we're dividing the two chi-squares, we end up with an F. So now we can just test on an F distribution, which basically is an illustration of us arriving back at what would be described as an extra sum of squares F test, like the ones that we would have studied back in Stat 378. But in general, like when we're doing this in an empirical setting and we have, output from a fitted model given an R and things like that, we're going to have estimates of the deviance. We won't need to take this kind of approach because we can just directly compute our delta D based off of those deviance estimates. But it's just kind of cool that we can also work around it theoretically. All right, so in this situation, we are going to have so this is going to become 658.770 sorry, 658,770 point 0.8 minus 652,424.5 divided by P minus Q. Okay. So that will be, I need to work this out somewhere. Okay, hold on. I'll just have to move this down momentarily. So given little n is equal to 24, little q equals 3, and p is equal to 4, then f is equal to the following over 1 divided by 6, 5, 2, 4, 2, 4.5 over n minus p, which is 20. And this is equal to 0.19. Okay. I mean, and clearly here, so continuing with the test. Oh, okay, so I'll just make a few quick notes here. So given f 0.19, that means that the p value for this test is going to be an f value, f, or the area above 0.19 on 1 in 20 degrees of freedom, which is going to be massive. Oh, it's not as big as I thought. I thought it would be much bigger. Is 0.667 or 668. So then on step 5, we do not reject H0. And then on step 6, just very briefly, at alpha equals 0.05, sufficient, no evidence that M1 is needed. All right. All right. Any questions? Okay, we did it. Okay, so that brings us to the end of lecture set 4. As I said before, a pretty heavy lecture set. Maybe too many examples, theoretical examples. But we got to see a lot of different illustrations, and it was really, I think, kind of a good throwback to what you might have seen in Stat 266, or you might even see in a higher level probability inference style class. We looked at the main takeaways from this lecture set are certainly how to conduct inference about the fitted GLMs. And for the most part, the statistic that we're going to focus on is the deviance measure. And we can do a lot with the deviance, as we just saw. So we can evaluate a fitted model compared to a maximal model, and we can also compare two fitted models via the deviance. We looked at, through the illustrations, what we did show is that the deviance structure changes with each of the different models that we are considering. So we don't have a consistent deviance formula for each of the different GLMs that we'll talk about in this class. The construction of those measures changes depending on the family of interest, or rather the distribution of the response variable. In general, larger deviances, so the bigger the deviance value, is an indication that the smaller model or the model of interest is insufficient compared to the larger model. And this would be true regardless of whether or not you're comparing to the maximal model or you're comparing two models of interest where the alternative specifies the larger of the two models. Right, in lab, we'll learn how to calculate the deviance directly. I mean, we'll look at a few examples of it, but it's basically just implementing the formula for deviance for each model. And then we'll see how, once we start fitting the GLMs, R actually outputs this value for us directly. And we'll start focusing more on interpreting these values and utilizing them like we have seen in these illustrations. On assignment number 2, there's a question that asks you to basically derive the structure of the deviance for a binomial style model. I think it might be a Bernoulli model. And using that derivation, you then have to compute the deviance at a variety of different points and then evaluate the models given those values. Okay, so that brings us to the end of lecture set number 4, which is great. So now we can move on to lecture set number 5. So now we're actually going to start talking about different types of GLMs and looking at more empirical examples, model evaluation criteria, or we'll talk about model evaluation, but we'll also talk about interpretation, the situations in which you would try using these different types of models, different options within the same family. So we're going to look at the most popular binomial GLM today, but there's actually 3 different binomial GLMs that are readily available in the software or in R and most software packages that fit GLMs. And we'll talk about comparison of those models, evaluation of those models using more traditional evaluation criteria like residual analysis. We'll talk about ideas like over dispersion, so what that means, why that could be an issue. And we'll also just look at model fitting and formulation and all of the different components that we've kind of built up theoretically to date. All right, so lecture set number 5 is focused on the logistic regression model. So we're gonna basically develop the binomial GLM, and then we're gonna talk about the structures of different types of binomial GLMs. So this is a situation where the response variable would be a binomial random variable. So a count of number of successes or number of outcomes over a certain sample size. And then we will discuss evaluation of the model, using the model, interpretation of the model, and all that sort of thing, inference based off the fitted model, given the model fitting criteria that we had built up in lecture set 3. Okay, so first off, just a little bit of background to set the model up. You'll remember the definition of a binary random variable. So a binary random variable is a value that is going to take on one number or one outcome or its complement. So in the general case, we can say Z is equal to 1 if it is a success, Z is equal to 0 otherwise. Okay, this success failure in this case can define a multitude of different situations, but the point is the binary value takes on 2 complementary outcomes, right? We write that the probability that Z takes on a value of 1 or is a success is equal to pi, and the probability that Z takes on the complement event is therefore 1 minus pi. Okay, and that would be by definition. And this gives us the PMF shown at the end of slide 3. Okay, so f of Z given pi is pi to the Z, 1 minus pi, 1 minus Z. This is just the PMF of a Bernoulli random variable. Okay, our interest is actually in modeling binomial outcomes. Okay, so you'll recall that if you have M Bernoulli outcomes where the response of each Bernoulli is a 1 or a 0, when you sum across those independent Bernoullis, you end up with a binomial. Okay, so that's where our interest starts, the formulation of our model starts. So we have a binary outcome, but we're actually modeling the number of total successes across, in this case, little m trials directly, right? So that means that the likelihood for our random variable of interest, which are the binomials, which we designate little y, is given below. And we've seen multiple illustrations of deriving this likelihoods to date. Okay. Okay, so just as a reminder, the structure of a binomial random variable. So if we have n observations, each observation is going to have a total number of trials associated with it, which we're calling little m in this case. Out of those number of trials, you're going to have some number of successes, which we're going to call little yi, and then we're going to have a corresponding number of failures, which is m minus y. Okay, so the total number of trials is equal to the successes plus the failures for each observation. So in our modeling framework, each observation is going to be a number of successes. It could also be a number of failures because we can find success from that. But basically, each observation is going to be the union of the number of successes and the number of failures. Okay, so we can have a different trial size for each observation. And of course, then we can have a different number of successes and a different number of failures for each observation. But each observation is essentially a pair, number of successes, number of failures. Right. When we construct a GLM for a binomial response, we're actually modeling the probability of success. So the output that we're going to get from a binomial GLM, it's actually you can get a variety of different things from it, but the main, or one of the most common outputs, is going to be the probability of observing the success, whatever that might be in the given scenario. Technically, you can also get the odds of that success. You directly would get the log odds. There's a lot of different things that you can take out of the model. It's very flexible in terms of interpretation. Right? So our response variable is going to be the couple of this number of successes and the number of failures. But our model, the binomial GLM model that we're learning about, so the logistic model, for example, is actually going to model the probability of success. But technically, it also models the odds of success, or the log odds of success as well. Okay, so it follows that the expected value of yi is going to be ni times pi I, because the expected value of a binomial random variable is n times pi. Okay, and then the expected value of little pi, which is our estimate of pi I, is going to be pi I. Okay. So the form of our binomial GLM is given in equation 1. So we have g of pi I. So we have some monotonic link being applied to the probability of success is a function of xi and then our model coefficients beta. All right. Setting up the link functions. In the simplest case, we can write that the g of pi I is equal to pi I. So we're using the identity link. The issue here is that this can result in outcomes that are outside the range 0, 1, which doesn't make sense because we're talking about the probability of a success. So we need to bound it between 0 and 1. In order to bound it between 0 and 1, we model pi I using a CDF. Okay, so this means that pi I is equal to the integral from -∞ to t of s ds. Okay? And we call f of s the tolerance distribution. This would be like the density function of the distribution that you're placing on pi I, and such that it integrates to 1. So these are just general definitions of any PDF. All right, so for example, let's consider the uniform tolerance distribution. So in this situation, f of s is going to be the density of a uniform distribution on the interval C1 to C2. Okay, so the density is given here. F of s is equal to 1 over C2 minus C1, as long as s is inside C1 to C2 and it's 0 otherwise. And you might recall that this is just a box between C1 and C2. So it follows that pi I, which is going to be the CDF of the uniform distribution in this case, is going to be the integral from C1 to X of f of S ds, which is X minus C1 over C2 minus C1. Okay. This results in pi I being equal to beta 0 plus beta 1 xi, where beta 0 is equal to negative C1 over C2 minus C1, and beta 1 is equal to 1 over C2 minus C1. Okay. So this is equivalent to a binomial GLM with identity link, but there's constraints imposed on beta and beta 2 to keep the value between 0 and 1. Okay, so this is just an illustration to show how the model can be formulated, but this is not a GLM, a binomial GLM that we're going to consider herein. A more common type of binomial GLM is the probit model. So this would be the binomial GLM with probit link. In this situation, you're going to assume that S is a normal random variable on mu sigma squared. And then we would say that pi is going to be the CDF of that normal distribution. Okay, so the result here is that pi I is equal to inverse of the CDF of a normal. So the link function is the inverse of the CDF for the normal distribution, which is equal to beta 0 plus beta 1 xi. And of course, this can extend more generally, is equal to X transpose beta. Okay. It doesn't have to be a simple linear form. It can be an MLR as well. Okay. In the SLR case, we would have beta 0 is negative mu over sigma, beta 1 is 1 over sigma, and then we have G pi is equal to sigma inverse pi I. Okay. So this is, again, the probit model, and it's one of the 3 commonly used binomial GLMs. All right, the second illustration is the when f of s can have density shown here. Okay, so then pi I is given by exp beta 0 plus beta 1 x over 1 plus exp beta 0 plus beta 1. So that means that we have a GLM logit of the pi function, which is the log of pi 1 minus pi is equal to beta 0 plus beta 1. And this is the logistic regression model, which is probably the most popular and most common type of binomial GLM. Actually, I think in R, this is the default binomial GLM. So you actually have to specify if you want to use the probit or the complementary log-log models within the GLM function, but it by default will fit this model to the data. All right, and again, the idea here is we want to model the probability of success. We don't want that probability to disobey the law of probabilities. So we're going to model, we're going to let pi I be equal to the CDF of some distribution such that the link function basically becomes the inverse of that CDF. Okay. So in the logistic regression case, when we fit the model, what you're actually getting out is the log odds directly. All right, and then the last one is called the complementary log-log model. So this is another type of link function that's commonly used when fitting binomial GLMs. Similar idea, suppose f of s has the form shown here, then pi is going to have the following, is going to be equal to the following. And that means that our GLM is going to be log negative log 1 minus pi equal to our model parameters. And this is the complementary log-log link. So there's 3 common types of binomial GLMs, the logistic model, the probit model, and the complementary log-log. In all 3 cases, the value that we're getting out, or the value that we'd be most typically are most interested in retrieving, is an estimate of the probability of success. So we're modeling the probability of success directly. But given that probability of success, you can also, for example, estimate the number of successes from the model. The drawback, though, is because the number of successes should be a whole number count, when you estimate these values, you're not going to get an exact whole number count. You're going to get a value with decimal places in it, like, for example, 3.476 successes, which doesn't have a lot of meaning, which is another reason why we focus on that probability, because that has meaning, because 0.997 has as much meaning as 0.7 in terms of a probability estimate. Okay, any questions? Okay, so let's start this example off in the time we have left. So we have an illustrative data set which counts the number of beetles that were killed at different dosages of carbon disulfide. Sort of a morbid example, but it works well for illustrating the binomial GLMs. Okay, so we have our sample size for each observation. So again, here, the observations are the couple of the number of beetles in the experiment and the number of beetles killed, or the number of beetles killed and the number of beetles that survived. That's how R sets it up anyways, right? So we have 8 observations here. So if we're able to model, if we have a data set where we're counting the number of outcomes directly, we can model this in a binomial context. That's one of the key takeaways. Okay, so this is a way for us to model expected number of outcomes of complementary events. Okay, so our response variable here is going to be the dosage level. So this is going to be X. And then yi is going to be, well, again, we're going to model the probability of success, which is going to be P equals yi over mi, right? So we want to model pi given xi. All right, so, here is a visualization of the data. Now, one of the key things that we can take away from looking at this is it's definitely not linear, right? So it's pretty obvious that the proportion killed, or the probability of death given exposure to the different dosage levels, is not linear. But you wouldn't expect it to be linear because the probabilities are going to be bounded between 0 and 1. So you would expect kind of like an S-like shape given the restrictions that are placed on those proportions, right? So this is not linear, more sort of S-like, which makes sense given restriction on proportion. Okay. Now, the other thing that we want to point out too is recall we use G in the GLM. G is a monotonic function of the response. So the fact that this isn't linear isn't actually an issue for us, because we're going to be transforming the response via G, and we just want to make sure that G is monotonic, and in this case it is, and it's increasing in one direction, which are the requirements of that particular function. So we're going to be able to account for this shape naturally through the link function. Okay, so I'll have to stop there, but what we'll talk about on Tuesday when we return to this section is formulation of the logistic regression model, and then we're going to study the output from that model. And then after that, we'll move into the next lecture set, which is evaluation and other types of GLMs. And then in lab, we're going to go through a whole analysis in R using these different models and talk about all of the different ways that we can compute the fitted values and the deviance measures and compute the residuals and study the residuals and all that sort of thing next Wednesday. Okay, so I'll stop there for today. Tomorrow in lab, we will go through the sample term test. And on Thursday, you will write your actual term test. And then we will return to lecture next Tuesday. So I will talk to you guys tomorrow afternoon in lab. And if you have any questions, I have office hours tomorrow morning, but you can also email me at any point. And I'll send a reminder with some details about the term test before Thursday. I'll be available for questions during the test as well. All right, so have a good couple of days and I'll chat with you tomorrow.